So for the last talk in the afternoon, we have Tamás Hausel, and he's going to talk about Hitchin map on very stable and even very stable upward flows. Thanks a lot.
Thank you very much, and thank you very much for the invitation. Before I start my talk, I wanted to show you a nice photo I just received of our institute, and partly to advertise our institute, because we are a relatively young institution, I think 15 years old. So this Institute of Science and Technology Austria looks like this in August. Here is the math department, my office. Here are hopefully some vineyards, and we are in the Vienna woods, so slightly outside, like ICMAT. But what is the institute? First, not far from Vienna, and second, it's a PhD granting research institute in the basic sciences. So we have mathematics in particular, and we concentrate on research and educating PhD students. And what's crucial is that we are still growing. For next 15 years, I think we have secured growth. So the institute is going to hire in the next 15 years for sure, new professors, postdocs, and PhD students. So anyway, this was just a short advertisement. Let me show you another picture which I found for preparing for this conference. And in fact, this was a conference which was in the Bernoulli Center at EPFL 2016, 6.5 years ago, which is, you can actually trace back my interest turning basically back to this kind of mirror symmetry questions that I will be discussing. So this one was a retreat, was nicely called Retreat on Higgs Bundles, Real Groups, Lagrange Duality, and Mirror Symmetry. The only information you can find about this on the internet, which I was just doing this search, not even this fact that it was organized by Oscar. I found some emails, so actually I know now the program, but on the internet, this is the only thing you have. This picture, in fact, I took during this conference. I really enjoyed this circle of ideas, possibilities, how to explain the geometry of real Higgs moduli spaces, or Oscar doesn't like it like that. So the moduli space of Higgs bundles for real forms, inside how to understand their geometry using mirror symmetry kind of ideas. And I really like this picture because I was actually sitting there next to the window, and you can actually see out way many buildings away through that window, but you had this beautiful tree. It was, of course, winter. And I think it's a nice allegory. Still today, we don't completely, or I would say, we hardly understand these kind of mirror symmetry explanations of the geometry of Higgs bundles for real groups. But today I will show something which I hope will start to be going to that direction. So let me very quickly just bring up these ideas very sketchily. Usually I apologize at this point that I'm going to be very sketchy, but that usually means still 2 or 3 slides. It's going to be 1 slide. So very roughly, we are looking at the moduli space of semi-stable, some sort of G Higgs bundles on a curve C, where G is some complex reductive group. And then the mirror symmetry, at least some simplification of it, some sort of classical limit of the actual mirror symmetry, which the physicists I will mention in a moment, Kapustin and Witten, explain, will give you the geometric Lagrange correspondence of Drinfeld, Lomon, and others. So it's a simplification. We are just talking about coherent sheaves on the moduli space of G Higgs bundles, which, roughly speaking, should be equivalent with coherent sheaves on the moduli space of G dual Higgs bundles, where that's the complex Lagrange dual group, G dual. And we roughly know how it should behave over regular locus, say. The generic fibers are abelian varieties, and it turns out to be dual abelian varieties. And then it should be some sort of relative Fourier-Mukai transform generically, but always the challenge is to extend it to more and more singular loci. I will be, in fact, interested in these directions. So I actually, all my interests are in the most singular fiber of the Hitchin map. Okay, so one important point, or at least mathematicians' interest, is to understand this pairing of objects. So you have some sort of geometrical objects in the left. If it's just the structure sheaf of some Lagrangian subvariety, then the physicists are telling us that they expect the mirror to be a hyperhomorphic vector bundle on the mirror moduli space. So what's exciting here is that we can imagine, and in fact there are many constructions of complex Lagrangians in these moduli spaces, and that conjecture seems to say that there will be as many hyperhomorphic vector bundles, but these animals are much harder to find. They are much more rigid. As far as I have intuition about them, they are more like hyperkiller manifolds themselves, which are not easy to find in general. So let me show you two examples of these Lagrangians, which will appear in today's talk. So one is exactly these moduli spaces of Higgs bundles for real forms of these complex groups. So for each of them, you will get a Lagrangian. And the other one of the examples we will be looking at today will be upward flows from Hodge bundles from fixed points of natural cis direction. Those also turn out to be Lagrangian. And then you can ask, what are their mirrors? They should be some sort of really non-trivial hyperhomorphic vector bundle on the duo. So I am sure in the audience there are people who understand whatever is known in the first case completely, but as far as I understand, it's still quite widely open. For example, there is this beautiful conjecture can be found in this paper of Baraya-Shaposhnik. It appeared in 2016, but in this conference, this was already known. I think the preprint is much earlier. So we actually partly talked about this conjecture, and the conjecture says that at least the support of the mirror of the structure sheaf of these Lagrangians attached to a real form of G should be something which is pretty delicate in the Lagrange world. Namely, the support should be the moduli space of Higgs bundles, which is now a complex group. So this dual of the real group will actually be a complex reductive subgroup of the Lagrange dual group. And amazingly, this was constructed in the thesis of David Nadler. And this is really sophisticated Lagrange business. He looked at the affine Grassmannian over the reals, and he managed to study their intersection chronology, perverse sheaves on it, and managed to find some sort of analogous picture to the geometric Satake equivalence. At any rate, in some super abstract ways, he cooked out this group, which we now call Nadler group. He has a table, and then you can see in any time people had worked out the mirror. So in some cases, Nigel has for U and N, for example, Nigel has nice actual construction of the conjectural construction of the mirror, a beautiful hyperhomorphic connection, but often we just know the support. And then it matches, but it's really unintuitive. So look at the table. Now I start to understand a little bit more, but it's really mysterious, and I love this mystery, and also the potential link to the Lagrange world. And this is real groups, so even better than complex groups, because that's much more Lagrange when you start to be for the reals. Okay, so I was very much excited by this, this was discussed. So it was Oscar, Nigel, but it was also Engo and Lomon giving talks, and Nadler was there too. So Jeffrey Adams talked about the real thing. I wish actually I could retake that retreat again, because maybe I would understand more now. Anyway, so, and the other one, which actually came up in our joint work with Nigel, this connection has to do with the other Lagrangian upward flows what is their mirror. We still don't know, of course, most of the cases we don't know, but at some region, at least, we have a pretty good picture, namely at the top of the Hitchin system, on the around the Hitchin section, which I will explain. And then, in my mind, it was retrospectively, I think Nigel was closer understanding that what we are doing has to do with Hakka operators, but at the beginning, I was just looking at these upward flows. But anyway, now retrospectively, this is how I explain why the Lagrangian upward flows have to do with Hakka operators. Is this suggestion by Kapustin and Witten that, first of all, you have to construct these Hakka operators, and they are really non-trivial. How you construct them. With Nigel, we looked at some of the simplest Hakka operators, and what people usually do, look at these elementary modifications. These are corresponding to the fundamental weights for GLN, but you can actually do a Hakka transformation for any dominant weight. And then I just write these operators. I mean, they are not exactly well defined. There's definitely disclosure one, I think, is the real issue, at least in my mind, to understand. Without the closure, I think it can be understood, but with the closure, it's much, much trickier. Anyway, it's some sort of elementary modifications on your, well, first on your Higgs bundle. So this will also act on Higgs bundles. It will be a correspondence between the Higgs moduli spaces, and using the correspondence, you can pull back and push forward coherent sheaves. And then the exciting thing is that, okay, this is actually pretty interesting geometrically. It will be obviously related to these upward flows, but why it's really so interesting mathematically, because physicists tell us what these Hakka operators should be mirrored to. Namely, they say they should be mirrored to Wilson operators. So Wilson operators, as we mathematically would define them, is much, much easier to understand. In fact, here is the definition. You take the universal G bundle, okay, which you maybe have to do it in some stacky sense, because it may not exist over the moduli space, but let's not go into that. Just imagine we have a universal G bundle for the Lagrange dual, G-check bundle for the Lagrange dual group, and the mu will label irreducible representations of it, and we will take the vector bundle in this representation, the associated vector bundle, and we restrict it to a point C. By the way, I didn't say it, but all these operators are at a point, at a fixed point, and you just tensor with this vector bundle. It turns out, by the way, that it is a hyperholomorphic vector bundle. Nigel, I mean, it's on our paper, so it's a nice. I call this a BBB operator. This is a Lagrangian operator, something like this we also discussed in the paper, that it preserves Lagrangians, the Hakka operators, and this one preserves hyperholomorphic stuff. Okay, and the cool thing is that they should somehow be mirror. So under mirror symmetry, they should intertwine like this. And then, okay, and then again, retrospectively, I am saying that there is a simple sheaf which we can apply this intertwining, namely to the structure sheaf. That's the simplest sheaf you can imagine. On the right-hand side, we will just have this one, the universal bundle itself, at that representation at that point, and its mirror. Then we would be saying that we first take the mirror of the structure sheaf, which again is something, the only thing basically we might know, just guess from this fiber by Furimuki transform picture, that the mirror of the structure sheaf should be the structure sheaf supported at the identity elements of the Hitchin fibers, and they form what we call the Hitchin section. And so therefore, this actually gives an explanation of what the mirror of the Hakka transform of the Hitchin section should be. Namely, it should be, okay, when you close it down, this is a hard operation, but the mirror of that should be this universal bundle in the representation labeled by the mu. So what's exciting here is that you will see that here on this side, we will be just looking at upward flows, because one observation is that if you take the Hakka transformation of the Hitchin section with some mu, then you are going to always end up at an upward flow of a given Higgs bundle. And in fact, you will get the whole upward flow. So the upward flows, at least on the top, at the top of the nilpotent cone, will be type 1,1 in the GLN case, will be the ones we can reach with Hakka transformations easily. I mean, yeah. Okay, so now this was the motivation. Let me start with something more pleasant and simple, just to discuss these upward flows. First in an abstract setting, I mean the general setting, and then in the specific setting for the Moduli space of Higgs bundles. So this circle of ideas was originally by Bielinski-Birula developed for smooth projective varieties, say, and then there were many extensions over the year. I am promoting this, so Carlos Simpson and Nakajima and other people have looked at similar extensions of the Bielinski-Birula theory. So we look at a complex semi-projective variety, and the second, this one semi-projective means that we have a C-star action, so it includes, the structure includes a C-star action on the complex algebraic variety, which satisfies some things. So for example, it's a quasi-projective, but in the stronger sense that in fact you can embed X into a projective space where you have this linear action on the projective space and you have an equivariant embedding. So the action is linear. This is always true if the variety was quasi-projective, in the sense it has one irreducible, for example, but sometimes you want not just irreducible ones. So anyway, then you have the assumption that the fixed point set is projective. And then the crucial one for the Bielinski-Birula to work at least semi in half of the time is that we will proceed that the half of the limits will exist. Namely, if I go to 0 for every at every x, and then I apply lambda to my point x, then I'm going to have a limit point. If it was projective, I would obviously get this limit point, and I would also get the upward limit point. But in the semi-projective case, we just have we assume only the existence of the downward orbits to have a closure point. So just two examples to bear in mind. The abstract example, which is pretty much giving the good idea about the local behavior, is cotangent bundles of, say, smooth projective varieties. That's an example where C star acts with a weight 1 along the cotangent direction. Higgs moduli space is our main example. Then Kuiper varieties of Nakajima and others. So now we introduce these upward flows. So these are the points in the space whose downward limit is a fixed point in the space, and it naturally has to be a fixed point by the C-star action. So you take a fixed point by the C-star action and you collect all those points which flow down to that point. And then it turns out to be a nice subset. I mean, it's just as it stands is a subset. It's called the upward flow from alpha. These are the ones flowing down to alpha. So from alpha, we have to come up. And similarly, you can define the downward flow with the limit upwards. But of course, that one will not always exist. But what's crucial is that at smooth points of your variety, when you have tangent spaces and everything, you can prove that both of the upward and downward flows are actually locally closed subvarieties. And you have a infinitesimal description, I mean, a complete description of these upward flows. They are actually isomorphic to vector spaces, and this isomorphism is even C-star equivariant, and this is also very useful for us because we know C-star action at these fixed points. I mean, we know the Hitchin moduli, Higgs moduli space, so it's very, very useful. So it's a C-star equivariant isomorphism. The only thing about this is not canonical. So you don't have canonical coordinates on here, which makes this isomorphic, and that will be part of our business here, try to find good, nice coordinates where, for example, the Hitchin map on them is nice. So now, because of the assumption of semi-projectivity, the upward flows will cover the whole space. So everyone will have a downward limit point, so it will belong to one of the upward flows. So we get this partition. And this partition is even nicer if you assume that the variety, okay, here I should take the smooth part, smooth locus, because I don't assume smoothness for the total space. So the smooth part of the variety, if it has a symplectic form, which is homogeneity 1, in this sense that that it rotates the symplectic form just by scaling it. In that case, many of these spaces and subspaces will actually be Lagrangian. So this positive part of the tangent space, so the C star will act at a fixed point, you pick out the positive weights, it will be a Lagrangian. If you take all the negative ones plus the 0 ones, so the 0 is in the fixed point set direction, that's also going to be Lagrangian. They are somehow complementary with respect to the symplectic form. Then if you now go to the space, then these upward flows, this ones, the upward flows will always be Lagrangian, and so will be the downward, what we call the, I forgot what was my terminology, but anyway, this, if you collect all of them, then because you have to take right to the also the 0 direction, this one will be also Lagrangian. Okay, and now if you put them, these downward flows together, all of them, then you will get a subvariety, in fact, a closed subvariety called the core of the semi-projective variety. It has the nice property, okay, it's in the smooth case that it's a retraction of the whole space. So the cohomology of this core is everything, but it's a Lagrangian subvariety inside X. And finally, the new set of ideas include this notion of very stability. And this actually makes sense already in this general discussion. So we will say that a fixed point of the C star action, smooth fixed point, or the upward flow itself is very stable, if and only if the upward flow is not just locally closed, but it's actually closed. And okay, this sounds like a definition, but it's actually quite natural. One way to reformulate this is to say that the upward flow does not have a non-trivial intersection with any other downward flow. So the intersection with the core is just the point itself. So there is nothing which will go up and hit some other fixed point of the C star action. And that's a nicer notion. Maybe that's, oops, yes. So that's the abstract story. Let's apply all this to Higgs bundles. So Lagrangian upward flows for Higgs bundles. I will be a bit more specific about these Higgs bundles now. We will take a smooth projective complex curve, I guess typically genus bigger than 2. And then we will just look at GLN Higgs bundles, which is just a rank n vector bundle together with the Higgs field, which is an endomorphism valued 1 form. That's the so-called Higgs field. And then we will look at the moduli space of semi-stable degree d. So we fix some integer d. I mean, this d will vary. That's a crucial property of the Hakka transformation, that it does not preserve degree or even semi-stability, which is an important aspect. Anyway, but we just don't say much about this. And then we take the moduli space of semi-stable such Higgs bundles. Again, it has a long story. Carlos Simpson, Mitsure gave an algebraic geometric construction. Nigel gave a gauge theoretical construction. Anyway, so these are very nice moduli spaces. And we have the C star action, which will make it semi-projective, so the Biernitsky-Birula theory can be applied. We can just scalar multiply the Higgs field. It's also going to be semi-stable. And the effect is that it's a semi-projective, which actually you can see it easily if you look at the Hitchin map. The next important player in this talk. So we take, in this case, just the characteristic polynomial of the Higgs field, and then because it was assisted by the canonical bundle, the coefficients of the characteristic polynomial will be sections of powers of the canonical bundle. At any rate, the point is the base is going to be a vector space, and the map turns out to be C-star equivariant if you have C-star action with weight 1 here, weight 2 here, etc., weight n on the base. The Hitchin map is C-star equivariant plus it's proper. That's again a theorem of many people. And the two together, in fact, imply that it is semi-projective, if you think about that. Okay, I just write it out. And then another beautiful property of this map, that it is an integrable system with respect to a natural symplectic form we have on the Higgs moduli space. And it was actually in the same year, in the same journal, maybe even in the same particular issue, another paper by Gérard Lomond, who has proved independently of Nigel's work on the integrable system. It's just that the nilpotent cones, so those Higgs bundles where the Higgs field is nilpotent, that is Lagrangian, which of course follows basically from Nigel's integrable system property. But Lomond gave an independent argument. And we could also give an independent argument now, because we can just prove, it's not hard to prove again from properness and C-star equivariant that the nilpotent cone, at least it turns out to be, and this is important for us, it's a subscheme. It has a non-trivial, non-reduced scheme structure, but if you take the corresponding reduced subvariety, then it's the core of M, which actually is again Lagrangian by this general Biernitsky-Birula stuff. So anyway, so that is we're just recalling the history, and I can also tell you why Lomond, in a moment you will see why Lomond was interested in this, what he used this for, because now we will be able to define very stability for the upward flows. So we know that the upward flows partition the space. Now we include even the strictly semi-stable ones, so there are some non-vector spaces here. And okay, actually I should have a smooth one here. So we will have a smooth, strictly a stable Higgs bundle, fixed by the C-star action, which Hodge bundle we call after Carlos Simpson. It's very stable. We actually have to assume stability, unlike for vector bundles, if and only if this upward flow is closed. Otherwise, this thing is not in our moduli space. And then you can see that this is equivalent. Partly, you can also argue from the general story that the core will intersect the upward flow in the very stable place if in just one point. So, but it's actually the notion of what Lomond was interested in back then, at least for some particular Higgs bundles. So those bundles which don't support nilpotent Higgs fields. So anyway, for us, one more important equivalent statement is that on the upward flow, the Hitchin map we restrict as a proper map. And this is actually the map we will be interested in trying to understand, trying to find coordinates on these upward flows, understanding the Hitchin map as explicitly as we can. It's a beautiful proper map between, I mean, algebraic geometrically, it sounds super simple. It's just two vector spaces of the same dimension. You have C-star actions, which you actually understand on both cases, but it turns out that these maps are really non-trivial. So Nigel, for example, found families of them appearing, and then you will see that some unexpected relations will also be encoded in these Hitchin systems. So just to close the previous story, to motivate Lomond's, he was interested in very stable Higgs bundles in our sense, in the case when the Higgs field is zero. So Lomond only cared about vector bundles, and then very stable vector bundle means that there is no nilpotent Higgs field. And this argument was used that if the nilpotent cone is Lagrangian, that means that intersecting it with one of the components will be strictly a subvariety, so it will have a dense open complement. So most of the vector bundles will be, almost all vector bundles will be very stable. But again, we cannot really construct things. I mean, you will see perhaps in Nigel's talk, he does look at explicit examples. Sometimes they can be understood explicitly. Okay, so this is one of the motivating problems on or side projects, or it's an important project, very interesting to write down, find explicit coordinates so that this map becomes explicit. And so the first set of examples, so there is this set of examples when the Higgs field is 0, but this in my mind is in the bottom of the nilpotent cone. We are going to concentrate on the top. There is a very interesting story down there. You will see some of it in Nigel's talk. But let's concentrate on the top. So there is one super famous Higgs bundle, which is supported on this vector bundle. And first, I'm not actually saying just the vector bundle itself. I will actually take all of the vector bundles on the upward flow from that one. And for this is just the companion matrix of these coefficients of the characteristic polynomial you take, you parameterize the base with. You can actually construct explicit matrices whose characteristic polynomial is exactly these companion matrices. And it turns out that if this was 0, all of them were 0, then this is what we call the canonical uniformizing Higgs bundle. Then all the other ones will give you precisely the upward flow from this one. And all the other ones together is going to give you a section of the Hitchin map, because each of them will have a characteristic polynomial given by that point A. So it's pretty tautological. It's a section of the Hitchin map. And in fact, you can argue that because of that, it has to be closed. So it is the first example of an explicitly understandable Higgs bundle, which is very stable, the canonical uniformizing Higgs bundle. Okay, now let me show you a whole variety of other examples, and they will be what we call in the paper type 1-1, Higgs bundles, because of course, if you have a fixed point of the cis direction for GLN, then you have an automorphism of the vector bundle undoing the cis direction. So anyway, so you will have a decomposition of the vector bundle into lines, sub-vector bundles, direct sum, and the Higgs field will be going down. And then one extreme case, there are two extreme cases. One is the one we looked at before, when the decomposition is just the whole vector bundle. In that case, the Higgs field has to be 0. And the other extreme is when these are line bundles. And let me show you how we parameterize these line bundles, which vector bundles, Higgs bundles of type 1-1. We take n divisors on the curve. The first one could be anything, but the rest is important. They are effective divisors, so they are supported at some point with the positive non-negative coefficients. And then we cook up this deformed vector bundle. So we get this one when these are all the trivial divisors. And then the point of doing this is that now we will be taking them, defining sections of these of the line bundle given by this divisor. And again, I is so we are in this effective case. And then we will form these lower triangular Higgs fields, which only non-zero below the main diagonal, and they are exactly given by these defining sections. And then you can check that these vector bundles are correctly, these line bundles are correctly chosen, so that you get a map, a Higgs field like that. And it turns out that every type 1-1 stable or semi-stable Higgs bundle looks like this, and there is some non-trivial stability condition to check. Okay, what else? One example, important example, usually I just play with these in the talks because it's just too complicated to have this, but today I wanted to make a point where it makes sense to look at the most general case. Anyway, one of the easiest set of examples when all these divisors are trivial. If all of them were trivial, then we would be down to the canonical uniformizing Higgs bundle, but we only have one of them, not the first one, but any other one, the case one, to be to be just a point C, and that I call EK. These are fixed point of the cis direction. I believe independent of the genus, but I haven't checked this. If these are if genus bigger than 1. They are always stable, but we always assume that everything is stable, and we can always let G goes high enough, and so we will get, we can consider all these cases at the end. And so let me now tell you the theorem. So we classified in the paper with Nigel all the very stable ones of this form, and the result actually is pretty neat. We prove, actually it's an if and only if statement, that a type 1,1 Higgs bundle, provided it's already stable, is very stable if and only if the last n-1 divisors together are reduced. So this means that every single point of the curve, at most one of them can be non-trivial, and even that has to be a reduced divisor. So it's a neat formulation, but you will see that in fact you can reformulate this, which is much closer to the spirit of these Hakka transformations and representation theory. But let me then give you one example. So of course, if there is just one point, which multiplicity 1 of one of the Higgs fields, then that is, this one is going to be a reduced divisor. So that's an example. The EKs are very stable. For example, and we will actually discuss what is the, how can we model the Hitchin system on these particular ones. Okay, so now Hakka transformation. So let me just, this is gonna be a bit technical, but let me motivate you that Hakka transformations are actually very useful. Both, I mean, we saw it in the talk of Jorn that already vector bundles, obviously, they have been looked at many times, starting with Narasimhan Ramanan, I believe. So we actually had to go back to sources like that because, for example, for Higgs bundles, you cannot find too much in the literature. I mean, Kapustin Witten, of course, talk about them, but I would like to advertise the use of Hakka transformations for Higgs bundles. Here will be for us interesting application, and also in the both recent proofs of the P cos W conjecture, Hakka transformations for Higgs bundles are used in a crucial way. So very important, and it's kind of elementary, really. They are called elementary modifications, but they will have a beautiful structure, and I will show you one of those structures here. So I remind you the theorem. I'm going to try to sketch how this reducedness arises. So first, let me define these Hakka transformations. The easiest ones, the case elementary or the case fundamental Hakka transformation, we can do for a Higgs bundle at a point of the curve if we can find a k-dimensional subspace of the fiber of the vector bundle at the point C, such that phi lives invariant that subspace. At this point, then you can make a Hakka modification. And when you do modifications, elementary modifications of vector bundles, then you don't have this condition, obviously, but this condition turns out to be a super interesting addition to Hakka transformations. And then if you have such a choice of a subspace, you will get a natural surjection of sheaves to the skyscraper sheaf at the point C. You will have the kernel sheaf, and because of the invariance of the subspace by the Higgs field, actually the Higgs fields will also induce Higgs fields for the kernel, and then at the end you can show that everything is actually here a vector bundle. I mean, it's a subsheaf, but it's locally free, going to be a locally free subsheaf, and you will get this Hakka modified Higgs bundle. Okay, and so this is what we call the Hakka transform, and we will, you remember, we label the Hakka transformations by dominant weights of the Lagrange-Zuel group. For us, it's just GLN by dominant weights. This is the case fundamental representation or dominant weight. And at this V, we will get this new Higgs bundle, elementary transformation. But now you think of these operators as acting as correspondences, so you allow to change V's. And then in that sense, you can see that any type 1,1 Higgs bundle and its upward flow can be obtained by successive Hakka transformations from the canonical uniformizing Higgs bundle and the Hitchin section. Right. Yes, so okay, so now I'm going to rewrite this data of the vector of divisors, which was in our paper with Nigel, to something which will reflect more the representation theory, and in fact it will hopefully clarify the reason why this, what does this mean, this reduced divisor, because we will replace this data of the vector of divisors as a map from the curve to dominant weights of GLN. For us, we have just the fundamental weights, omega 1 to, well, omega n. So omega n is the determinant, so it behaves differently from the rest. So dominant weights are allowed to have only non-negative coefficients for the first n-1 fundamental weights, and the last one can be anything. So anyway, this is the set of dominant weights, and we imagine that every point we attach one of these. Finite support means that almost all points, I mean, finitely many, except finitely many points, this is the 0. There is nothing else. And then we are going to construct or think about the Hakka correspondence. So the Hakka correspondence actually is the one which is labeling these data. So at the point C, I check which combination I have here, and then I will do the Hakka transformation at that fundamental weight. And then if it is the top one, then it's just tensoring with OC. So it's you can do it both ways. So you have a Hakka correspondence, Hakka operator, and then you can argue that the image of the Hakka correspondence of the Hitchin section will be precisely the upward flow from a type 1 Higgs bundle, where I am actually giving the vector of divisors from this data. So you can just take at the point C, you take which fundamental representations appear, and right, with what coefficient, and that's going to be your divisor. Anyway, there is a dictionary between these mu's and or deltas. And the second observation, and that's really where the really non-trivial thing happens, how do you understand if you have a Hodge bundle, a Higgs bundle fixed by the C structure in the closure of another upward flow? And so what we can prove, or what can be proved, is that if this happens, that one Higgs bundle is in the closure of another type 1 Higgs bundle, this means that the corresponding dominant weights are less than or equal to the next one. And this one is a very interesting and non-trivial partial ordering, and this is amazing even to understand that somehow the upward flows of Higgs bundles, the way how you close them, are actually just mirroring this partial ordering among dominant weights. Let me give you the partial order. First, I am actually giving you how to go from the vector of divisors to these mu's. So here is the formula. And then what's more crucial is what's this partial ordering between dominant weights. We say that one dominant weight is greater or equal to the other if the difference can be written as a non-negative combination of positive roots. So that's surprisingly sophisticated, even combinatorily, these kind of definitions. So there are the roots, there are the weights, and then it's kind of interesting and non-trivial how the root lattice lives inside the weight lattice, and then the roots, positive roots, play a fundamental role here. But okay, so but now if you believe this, then you see, or you can argue that in order to be very stable, meaning that there is no one in your closure, it can only happen if you are minimal with respect to this partial ordering at every point. So minimal with respect to this partial ordering dominant weight is called minuscule. So this means that something is very stable if and only if the dominant weight we attach to a point is always minuscule at every point. Typically 0, which we also consider minuscule. That's minimal with respect to this. So that's somehow at the cone of the dominant wide chamber. But there will be other ones. And in the case of GLN, these other ones are precisely the the fundamental weights. So the fundamental weights are precisely the minuscule ones. It's again another non-trivial fact, something which actually will not be true for other types. So that actually concludes, because this, in this sense, minuscule means precisely that at a single point, I can only have one of the fundamental weights with coefficient 1. And that translates to this reducedness. Okay, so that was what we did with Nigel, and actually these kind of things it happened afterwards. And let me now show you a further progress that I can now understand the upward flows on particular very stable type 1 Higgs bundles. And for simplicity, you will see we will take EK, these ones, in terms of equivariant cohomology, in this case of Grassmannians. And so first, to motivate, I will recall what equivariant cohomology is, and I'll try to show you how this may be a good model for the Hitchin system, equivariant cohomology of a Grassmannian. Okay, in general, I will be talking about equivariant cohomology. So again, just a quick recall. So you take, here it's algebraic geometry, you can take a compact group if you prefer. This is homotopy theory. So we take a complex reductive group, the corresponding universal principal G bundle. What will be important is somehow will be the Hitchin base in this model. We will take the equivariant cohomology of a point, the cohomology of the classifying space will be your coefficient ring. And this is actually just like the Hitchin base is a vector space. And in fact, in a very similar way, it's a vector space. It is non-trivially a vector space. It's the quotient of a vector space, namely I'm talking about, of course, the spectrum of this algebra. As an algebra, this is going to be a polynomial ring. This is the Weil invariant part of the functions on the Cartan subalgebra. Well, anyway, geometrically it's a vector space. And then now we are going to take any variety and this group G acting on it. And you know, when you do the equivariant cohomology, we like this Borel quotient thing. And then we will define the cohomology of the Borel quotient. By the way, we always take complex coefficients in this talk for cohomology. That's what we call equivariant cohomology. And inside this geometry, we already see that this Borel quotient fibers over BG. So this is actually an A* G algebra canonically. And I claim that this looks like a Hitchin system if you look at the spectrum of these algebras. And especially in one case, it will be very interesting, namely if the variety or the topological space is equivariantly formal, which one way to define it is that if you localize to the origin inside, you take the preimage of this map will abstract over the origin, you should recover the ordinary cohomology. There are many other equivalent ways. For example, that this algebra is free over the base. Anyway, so if the space is equivariantly formal, then we actually have something like a very stable upward flow with the Hitchin map, because we have the spectrum of the equivariant cohomology mapping down to the spectrum of the base. And the base is like the base of the Hitchin system. The Cartan Sabal, the algebra of the maximal torus time over the Weil group. And this map will be proper. And this map is going to be our model for the Hitchin map in particular cases when the variety in this talk are just the Grassmannians, or more generally minuscule or actually cominuscule flag varieties. So I'm just telling you the theorem in this case of GLN for these upward flows from these baby versions of when you just have one point of the curve, and that point you only have the kth of the divisors is non-trivial. So in the Higgs field, you only have ones everywhere below the main diagonal set, one point where you have the defining section of OC. So that's the upward flow from that. And the statement is that you can model the Hitchin map on this. You can find coordinates on the upward flow, that the map down to the Hitchin base is modeled by the equivariant cohomology effect Grassmannian in this sense. So these maps are pretty explicit how to define. So you take the point in the Hitchin base and you evaluate it at your point. You're actually going to have a point in here, and this is just the pullback diagram. You will get something here, and the statement is that it is isomorphic with the upward flow of the Hitchin system. So amazingly, I mean, I start to understand how does this come about. Originally, I just noticed this as a fact that the Hitchin system can be modeled by the spectrum of equivariant cohomology of this Grassmannian. And of course, the answer now is in mirror symmetry. But I'm not going to talk about the mirror symmetry today. But there is a construction on the mirror side where the equivariant cohomology also appears, called the Kirillov algebras, and that is pretty natural. And then you can understand that this finite map will be mirroring this bundle of algebras on the mirror side. Anyway, let me not go into there more. So just to demystify the appearance of the Grassmannians, the reason they appear, of course, because in that Hakka modification, if you remember, we were looking at an element in the Grassmannian, these k-dimensional subspaces of that fiber, and we wanted the Higgs field to preserve that. And that geometry of matrix, and the question is which k-dimensional subspaces it fixes. It turns out we'll bring in the Grassmannian, and now we have actually an independent theory about that, which explains that those fixed point schemes can be understood by the equivariant cohomology of the ambient space. And okay, it actually conceptually it's part of the affine Grassmannian. They are the easiest affine Schubert varieties. And one outcome of this, I mean, this was not the way how I discovered this, or because with Nigel we first started to look at not the whole map, just what's over zero, and I call that multiplicity algebra. So which is the preimage of zero. It's going to be a fat point. And to me, it's still really amazing, because after we finished the paper, that's where we started to think about these multiplicity algebras. The only thing we are looking at is how these very stable upward flows are intersecting the nilpotent cone. They are going to intersect it in a single point, but amazing, that single point is a fat point. And it turns out that the ring of functions on that fat point is understandable. And it's very interesting. I mean, here you get cohomology of Grassmannians, and Nigel will show you what you get in some small rank and genus cases for the it's really interesting and hard. And okay, and in this case, this you can deduce because of equivariant formality that over zero, indeed, we should see the ordinary cohomology ring of the Grassmannian. And that was very exciting in the beginning, because we had in the paper, we computed something called the equivariant multiplicity. And then I, of course, knew this is the Poincaré polynomial of the Grassmannian, but I didn't dare to imagine that the actual cohomology ring of the Grassmannian will somehow appear, but it did like that. Okay, so now let me come to 2 months ago. So Oscar has a master's student, Miguel, who was coming for an internship to IST, and he was already prepared with the real forms, Oscar's stuff. And I'm trying to tell him this is not how usually research looks like, but it turned out that from the very beginning we could actually understand things, and we had the right questions. So it was kind of a miracle, because 2 months later I can already show you some theorems. So we call them even very stable upward flows, and then I want to argue that even very stable upward flows really have to do with real forms, and in this particular case with inner real forms or Hodge type. As I'm learning, actually I started to learn all of this in the last 2 months. I didn't know that Carlos Simpson already wrote about them in the paper I thought I knew. Anyway, but for me, it's extremely simple. I actually first didn't believe when Miguel was trying to convince me that if I take this involution -1 on the Higgs field and the fixed point variety is Lagrangian. Even that I didn't believe it first, but it's not just Lagrangian. These are this UPQ moduli space is all of them at the same time. And okay, this actually goes back, they have a very nice theory which describes it in all types and everything. But I will not really talk about these real forms anymore. I'm just going to concentrate on how this -1 acts on the upward flows and how we can understand the Hitchin system with respect to this -1 involution. So, okay, we will look at the next slide the Hitchin system on the fixed upward flows, or the fixed moduli space on these, and now the base is going to be funnier, right? So now -1 acts on the base, and you have for GLN you have invariant polynomials in every degree, but this -1 action will kill the odd ones. So in the fixed ones in the base will be only the even ones corresponding to the even degree invariant polynomials. So already that changes. And okay, and this is the problem we started or I asked questions to Miguel. Can we understand upward flows in here? And then eventually how the Hitchin map acts on them, and how Hitchin map acts on them. Okay, so this is somehow very simple to think about, at least in terms of this this infinitesimal model. I told you, Bieliński-Birula proved that all these upward flows have a model like the tangent space at that point. And if you think about it, now we have just a vector space with the C star action, and you want to find the -1 inside the C star and take the fixed points, and then it's easy to convince yourself, I will prove it, that this upward flow will be precisely the parts where the weight is positive, even, right? So that's the first observation, is that the upward flows in the -1 fixed point set will be modeled by the even. So by 2+ I mean all weights which are even, positive even. So that's easy. That's why we call them even upward flows, because it's always just going up along the even weights. And now maybe you were thinking it was funny, the name, but okay, it's likely meant, of course, a bit. So even is a bad word. You will see soon. We will talk about even roots, and that's not something you want to check the internet about, because you will get everything else than what you are interested in. Now, anyway, so you have even very stable fixed point of the C star action. First of all, of course, everyone which is fixed by the C star will be inside. So when we study these even upward flows, we can start from anywhere. And then we say that it is even very stable if and only if the part of the upward flow in the -1 fixed part is going to be closed. It's a fair generalization, and it's equivalent that the upward flow, even if it will be the case, sometimes they will be not very stable. So there will be parts inside the nilpotent cone, but we don't allow even weights in the upward direction. Okay, let me tell you now the answer, which you might be guessing already, maybe, that there is a partial ordering on dominant weights, which take into account this evenness. And the definition is very simple. We will do the same thing. We will say that one dominant weight is less than or equal to the other if the difference can be written as a non-negative combination of positive roots, but not all positive roots, only positive roots of even height. So these are non-negative integers, and these are positive roots of even height. So what is height, if you don't know? I guess, that you write every positive root can be written as a linear combination of simple roots, and you just count you add the coefficients. And those, that will be the height. So you are looking at those here, those positive roots, which can be written with the use of even number of simple roots. And the answer may be not so surprising now, but this is a surprisingly, first of all, why we get to this was a complicated root, but the result is that in the same setup as before, so we will decode these type 1,1 Higgs bundles by this map mu from C to even to dominant weights. And it is even very stable if and only if at every point we have an even minuscule dominant weight. That means, of course, minimal with respect to this new partial ordering. And it's a really nice result. And the funny thing is that, so Miguel was first starting to find even wobbly ones. So he managed to look at the Hakka transformation ideas, and he found actually 2 families of even wobbly ones, and they didn't look anything to do with each other. We were guessing, we don't know, we didn't really know, are there other ones? And I have to recall at some point I had this idea about these even heights, and then I asked, by that time actually Miguel was even writing the partial ordering. So I asked him to so just draw, if I start to close down the upper flows, what's the partial ordering? So we had these graphs, big graphs, and then amazingly those graphs are precisely given by this partial ordering. So, and now we can prove it. So Miguel can prove the wobbly ones, and there is again a similar simple Hakka transformation argument to show that the others are even very stable. But look at this, there are many more even very stable ones, of course, because we just care about even weights. So for example, for GL2 there's only one positive root, and that is of course height 1. So there are no even positive roots, and so there is nothing here. So actually everything is very stable. And actually we know this, right? I mean, I studied Nigel's mirror symmetry construction for U11 and what should be the mirror. And then of course, and even U11, I think even looked at my PhD in terms of -1, fixed points of -1. And then you have these different components, they don't interact. And of course, any upward flow is closed. I mean, there is nothing. They are all disjoint. So it's not so surprising. But then there are many other more complicated examples which are obviously not minuscule, like this guy. This is the one example where I first tested, can I prove that this is even very stable? Namely, for example, you can have 2 twos. This is for GL4. What's important is the distance has to be even between them, otherwise it would be even wobbly. Anyway, so this guy is even minuscule, but not minuscule. In fact, it will intersect the upward flow in quite big dimensional subspace, the nilpotent cone, but all those directions will be either weight 1 or weight 3. Anyway, so that's a nice end of this classification. And in the beginning, already the very beginning, I started to think about, okay, let's assume we understand what are the even very stable ones, but what would the Hitchin map look like on them? So, and then we have this algebraic model of the equivariant cohomology of the Grassmannian, and the question is, what's the -1 fixed point set of the spectrum of the equivariant cohomology of the Grassmannian? So it's an algebraic question, but we will have a beautiful answer. So for simplicity, we work with even n, so GL2n, and then we have an even number between 2n and 0. And we are going to think about the minuscule upward flow, this one, which I had the theorem that it is modeled by the spectrum of equivariant cohomology of this Grassmannian. And now we actually know the -1, it just comes from the grading. Now you have to look at the ideal of generators. I mean, I don't know, many of you, I'm sure, most of you, everyone must have seen the relations in the cohomology of the Grassmannian. So, but you have to now take -1 fixed thing. So you have to throw out the odd degree generators. And what you get, it looks like also the cohomology of a Grassmannian, but all degrees are doubled. And then you can prove that that in fact, so here I am actually spelling out what you do. So you take the -1 invariant part on the ring of algebras. This is called the co-invariant ideal. So you take all the odd degree parts, you put it in your ideal, and you quotient it out. you actually get here precisely what we get in the Hitchin base, only the even degree invariant polynomials. And here, this is the trickier one. You have to throw out the odd generators. I mean, if you know the cohomology of the Grassmannian is generated up to degree k, say, so there will be odd and even generators. But what you are left with is amazingly has a beautiful description as the spectrum of equivalent cohomology of what is called the quaternion Grassmannian. So that was great. And then I started to look at other cominuscule or minuscule flag varieties, which again, we haven't really studied very carefully. But again, those should, the equivalent cohomology of those should describe the Hitchin map in those types. And then you have a beautiful picture. So you find two other families of, no, one other family and one exceptional case where this quotient is non-trivial. In any other case, the equivalent cohomology of the cominuscule flag variety is generated in odd degree. But in these two cases, you have, so you have for SO4 n plus 2, so it's D type. So this was A type, D type, and we will have one E type. And then the minuscule flag variety is this even quadric. It's actually pretty simple. It has a cohomology generated in odd degree. Okay, I always divide the degree by 2. So in H2, it looks like almost the underlying projective, in the ambient projective space, but in the middle, there could be, and there is a non-trivial cohomology, which in this choice, it's actually going to be even degree. And so that's why we have to choose this. And then what you get is that there's only one cohomology survives. But again, this you have a very nice answer that this will be the equivalent cohomology of the sphere. So it's only a two-dimensional rank 2 thing over the base, but it still has a very nice description as a symmetric space. And the final thing is the most exotic one. When you get a non-trivial algebra, where the cohomology ring is not generated in odd degrees, you have the E6 minuscule variety, which is the complex Cayley plane. So the Hitchin map should be modeled by the equivalent cohomology of this complex Cayley plane. And when you compute, again, I mean, I actually just looked at tables of cohomology rings. These things are known classically, I mean, Japanese people. And so actually, there was, I found Simon Salamon's birthday conference. There was a contribution which was very useful, Piccini or something like that, who has a very careful discussion about all these, the special flag varieties and their cohomology rings. Anyway, so you can then argue, prove that this, the -1 fixed part is actually, again, has a meaning in terms of equivalent cohomology. It's now rank 3. Right, this is like a projective plane, but it's like quaternioni. No, not quaternioni, but Cayley, whatever, octonioni. So finally, what you should notice here is the amazing appearance of the Nadler group. So all these groups which appear is going to be the Nadler group of the real form. And I don't think it's an accident, but I don't know the reason yet. And so let me just finish with some problems just by showing it to you. And thank you very much.
Thanks a lot for the very nice talk. Any questions?
Thank you for this very nice talk. Yes, you have a comment and a request.
Okay.
So precisely about the Nadler group that he constructed for real forms.
Right.
That was remarkable indeed, as you have mentioned. But as I think he realized, the focus was perhaps not, or maybe is not the best one to analyze in relation to our Higgs bundle problems. And perhaps better to think of the complex symmetric variety, that so that not the real form, not the anti-holomorphic involution, but the holomorphic one. And in fact, he and Gates colleague, some years later in 2010, constructed a group, a dual group, using some Satake, similar Satake correspondence, for spherical varieties, of which G varieties, of which the symmetric variety is one of the most basic examples. So I think maybe the focus should be in there. I don't know, but it looks to me. And in fact, this
but still mysterious. I mean, that
Sure,
the
sure.
story is the same. They do. I mean, they construct so they attach some sort of analog of the affine Grassmannian to these symmetric spherical varieties, and then they show that the category of Perber-Sheaves, monoidals, and Tanakian thing, there should be a. But it's still mysterious. So
it's very mysterious, but there is nothing real. So there's nothing. I mean, it has to do with the real groups, but it's just.
Well, we are already. I didn't do anything real. I just use your evolution, and
exactly.
you don't do
exactly. So that is very much in tune with what you say.
Yeah.
And my request, you did it only once, but because there are many native speakers here, various stability has to be found a better name. Various stable is fine, but various stability.
Stable was the name given by.
So that's my humble, but actually serious request.
What's wrong with this? I don't see.
The grammar is wrong. Various stability.
And in French, it's okay.
Neither in French nor in Spanish. That actually, or Italian.
But it came. I mean, in Lomon's paper, he calls them très stable. I'm not making this up. It's
no. The adjective very stable is fine, but various stability. That's my point. No, I'm sorry. No.
Sorry, I conjugate everything.
No. Yeah. That's my request.
Okay.
There are so many clever and native people in several languages. I'm sure that the term can be found.
American English, you mean?
Sorry, the even powers of the canonical bundle, you'll see those appear for the orthogonal and symplectic groups too, but presumably everything's different. And
I think those will be closely related. So,
but I mean, it's still curious. You're seeing it for the real forms, but you're also seeing it for these groups.
Right. So as I said, I mean, if you just take the Hitchin base and just interested in what's -1. Of that, then you get the even things, and yeah.
So here you're looking at the intersection of two Lagrangians, basically. So what does it mean in the mirror?
Right. So obviously, I haven't yet been able to. I asked this like the first question: what does it have to do with mirror symmetry? That now we understood. You are right. It's not the Lagrangian itself, the intersection. I had previously an idea. I mean, you suggested this first, and what could it mean, mirror symmetry? So when you do these pairing things, which I started to do in the beginning, when you pair two Lagrangians, well, I can compute the C star, the kind of indices, what Johan was talking about. I can compute the C star equivariant Euler form of the two things, and that should be checkable on the other side. But the problem is that the other side, I will have two hyperhomorphic vector bundles, typically. How do they say? I mean, full support, and then you have to do the integration on the whole Hitchin moduli space. It's much harder. But I hope that it will be somehow even nicer. I mean, there should be some. So maybe the Lagrange, the -1, maybe we can understand that that this -1, maybe that corresponds to something under mirror symmetry somehow. The involution itself, not the Lagrangians, but.
But I wondered whether there's just some obvious morphism from the vector bundle for one Lagrange and the vector bundle, rather than going the equivariant, this and that and the other.
Right. I haven't. Well, I mean, you are the only one who has a conjecture about the mirror of the whole thing, in the UNN case. Yes.
Okay, so I should work it out, I guess.
Yes, but yeah, it's very interesting, and I haven't yet. That's why the first question is I haven't yet managed to connect. It's 2 months ago we started. 2 weeks ago we finished when I had to give my abstract. And so, yes, I hope that we will have a nice story about that too.
More questions? No, let's Tamás again.